In the waning years of the 19th century, the edifice of classical physics stood as a monument to human reason. It was a vast, ornate cathedral, its foundations laid by Newton, its soaring arches built by Maxwell, its stained glass windows painted with the laws of thermodynamics. For many who worked within its walls, the structure was essentially complete. The great truths had been revealed. The task that remained was one of refinement, of measuring the known constants to ever greater precision, of polishing the brass fittings until the entire edifice gleamed with a final perfect light. The universe was a grand clockwork, predictable and knowable, its mechanisms governed by elegant, immutable laws that humankind was on the verge of fully comprehending. Into this cathedral of certainty walked a young man who did not belong. He was an outsider, a rebel, a thinker whose mind did not conform to the rigid architectural plans of the old masters. His name was Albert Einstein, and he was born in 1879 in the German city of Ulm, into a secular Jewish family that cherished intellectual independence above all else. His childhood did not foretell genius. He was slow to speak, a trait that deeply concerned his parents, but which perhaps allowed his inner world of concepts and images to mature without the premature constraints of language. He was not a prodigy who dazzled his teachers. Instead, he baffled them. The authoritarian, rote-learning discipline of the German schools stifled him. He questioned everything, a habit that was seen not as a sign of curiosity, but as a mark of defiance and disrespect. One teacher famously informed him that he would never amount to anything, a judgment that echoed the institution's inability to recognize a mind that worked on a different frequency. His true education began not in the classroom but in his own head, fueled by books and a gift for visualization. His family's move to Italy offered an escape from the oppressive German system. Albert, left behind to finish his studies, soon engineered his own departure, using a doctor's note to secure his release from a school he found intolerable. His next goal was the prestigious Zurich Polytechnic. He failed the entrance examination on his first attempt, a humbling experience that nonetheless revealed his prodigious talent in mathematics and physics. After a year of preparatory study at 16, he posed a question that would haunt him for a decade. What would it be like to ride alongside a beam of light? If he could catch up to it, moving at the same speed, the wave of light should appear frozen, a stationary oscillation of electric and magnetic fields. But the laws of physics, as he understood them, suggested such a frozen wave could not exist. This simple, elegant paradox was a crack in the foundation of the cathedral, a fissure no one else seemed to notice. A progressive school in Aarau, Switzerland, which nurtured his visual and conceptual style of learning, he was finally admitted. The Polytechnic was where he began to truly blossom, not by diligently attending lectures, but by devouring the original works of the scientific pioneers, wrestling directly with their ideas. It was here he formed a small circle of brilliant friends, most notably Michel Bessot and Marcel Grossmann, who would become his lifelong intellectual sparring partners and collaborators. It was also here that he met Mileva Maric, a fellow physics student from Serbia, a woman of fierce intelligence and ambition. Their relationship was a complex tapestry of deep intellectual connection, shared dreams, and ultimately profound personal difficulty. Upon graduating in 1900, Einstein found himself adrift. His rebellious streak and his habit of skipping lectures had alienated the very professors whose recommendations he needed to launch an academic career. For 2 excruciating years he lived in poverty, scraping by with temporary tutoring jobs. The sense of failure was crushing. During this period, he and Mileva married and had their first child, a daughter named Liesel, whose existence remains one of the most sorrowful and opaque chapters of his life. Born out of wedlock and into financial destitution, she was likely given up for adoption, her fate a mystery that would shadow Einstein for the rest of his days. The lifeline he desperately needed arrived in 1902 through the intervention of his friend Marcel Grossmann's father. Einstein secured a position as a technical expert, third class, at the Swiss Patent Office in Bern. To the outside world, it was a bureaucratic backwater, a dead end for a man with his ambitions. For Einstein, it was a sanctuary. The work was methodical and engaging enough to keep his mind sharp, but not so demanding as to exhaust it. He could quickly grasp the essence of an invention and spend the remainder of his workday lost in thought, his mind ranging freely across the cosmos. The steady salary brought a stability he had not known for years, allowing him and Mileva, now with their first son Hans Albert, to build a life. In the quiet solitude of that office in Bern, removed from the pressures and orthodoxies of academia, the seeds of revolution began to germinate. He was a patent clerk by day, a titan of theoretical physics by night. He even founded a small discussion group, the Olympia Academy, with his friends Maurice Solowijn and Konrad Habicht, where they debated philosophy, science, and literature, stoking the fires of his intellectual curiosity. The year 1905 arrived, and with it, an explosion of intellect that has no parallel in the history of science. In the span of just a few months, the 26-year-old patent clerk published 4 papers in the Annalen der Physik. Each one was a masterpiece, and any single one would have secured him a place in the pantheon of physics. Together, they constituted a complete reimagining of the physical world. His first paper tackled the photoelectric effect, a phenomenon that had baffled physicists. When light strikes a metal surface, it can knock electrons loose, but the results defied logic. The energy of the ejected electrons depended not on the brightness of the light, but on its color or frequency. A dim blue light produced more energetic electrons than a brilliant red one. Maxwell's wave theory of light, the bedrock of 19th century physics, could offer no explanation. Einstein proposed a solution so radical it bordered on heresy. He suggested that light itself was not a continuous wave, but a stream of discrete energy packets, which he called light quanta, and which would later be named photons. The energy of each photon was directly proportional to the frequency of the light. This simple idea explained the photoelectric effect perfectly. A single blue photon, carrying a high-energy punch, could liberate an electron. A red photon with less energy could not. Making the red light brighter just meant more low-energy photons, none of which had sufficient force. This was the first shot in the quantum revolution, a direct assault on the wave theory of light and the introduction of a granular, discontinuous reality at the smallest scales. It was for this specific insight, and not for his work on relativity, that he would eventually be awarded the Nobel Prize in Physics in 1921. His second paper was a powerful affirmation of a reality that was still, in some circles, debated. It provided a rigorous mathematical analysis of Brownian motion, the random, jittery dance of tiny particles suspended in a liquid. Einstein demonstrated that this chaotic motion was the visible result of the particles being constantly bombarded by the individual molecules of the fluid. By calculating the statistical properties of this dance, he provided a way to determine the actual size of the atoms and molecules themselves. It was the first direct, quantitative proof of the atomic theory of matter, taking a phenomenon that seemed random and revealing it as the visible fingerprint of an unseen molecular world. But these 2 papers were merely the prelude. The main event, the seismic shock that would bring the old cathedral crashing down, came in his third paper on the electrodynamics of moving bodies. This was the special theory of relativity. The problem that had obsessed Einstein was a deep and troubling contradiction at the heart of physics. Newton's laws insisted that the laws of mechanics were the same for all observers moving at a constant velocity. If you are on a perfectly smooth train, you cannot perform any experiment to tell if you are moving or standing still without looking outside. This is the principle of Galilean relativity. But Maxwell's equations of electromagnetism seemed to violate this. They predicted that the speed of light in a vacuum was a constant, a universal value, c. This created an inescapable paradox. If you were on a train moving at half the speed of light and you turned on a flashlight, common sense and Newtonian logic would dictate that an observer on the platform would see the beam of light moving at 1.5 times the speed of light. But Maxwell's equations insisted that the observer on the platform would still measure the light's speed as exactly c. How could both be true? The laws of physics could not be different for different observers. Einstein's genius was to realize that the problem was not with one of the theories, but with the fundamental common-sense assumptions about space and time that everyone, including Newton, had taken for granted. He decided to take the 2 contradictory principles, the constancy of the speed of light and the principle of relativity, and accept them both as absolute truths. He then followed them to their relentless, mind-bending conclusions, wherever they might lead. To make these 2 principles compatible, something had to give. That something was the idea of a universal, absolute time and a fixed, absolute space. Einstein showed that time is not absolute, it is relative. Your measurement of the passage of time depends on your state of motion.